Is it visible?
Yes, sir.
Yes, sir.
Yes, sir.
So quick short. So quick short actually it depends upon your divide and conquer approach. So there are several strategies for solving a particular problem. Okay. So there are several algorithms, design approach. First one is divide and conquer. Second one is dynamic programming, greedy algorithm, backtracking, branch and bound, etc. There are several design methodologies for solving a particular problem. So quick short depends upon the divide and conquer approach. Okay. So first of all, we have to divide quick short, merge short, binary search. Both of these kinds of problems depends upon the divide and conquer approach. So first of all, we have to divide the sub problem into small sub problems with size, each of size n by b. Okay. So we have to divide the array into b number of sub problems in each of size n by b. Here in case of quick short, merge short, and binary search, we are dividing the sub problem in two parts. Okay, that's why the value of b is 2. So that's why the uh, problem size is n by 2. Okay, the problem size is n by 2. Now quick short, as it depends upon the divide and conquer approach, so we have to divide the array into two parts here, and then we have to recursively call the functions. That's why it is a good example of your recursion. Okay. And actually recursion use the system stack, so it is a stack application also. Quick short, these are termed as partition exchange short. That's why this is the recursive version. Okay. Now there are the main idea behind the quick short is to find out the pivot point and place the pivot element in its appropriate position. Okay. So there are several partitioning methods. If you use the first edition of Corman, you can get the Hoare partitioning, the initial partitioning method of quick short. Hoare partitioning takes the first element of the array as the pivot point. Then you have to place the pivot in its proper position. Here in the third edition or second edition of the Corman book, use the Lomoto partitioning, where we choose the last element as the pivot. In case of randomized quick short, you can take any of the element as a pivot element. But finally, you have to place this pivot element in its proper position, right? Now, so these are the average case and best case behavior of quick short. N log n, which is lower than, which is better than insertion short, selection short, bubble short, n log n. But the worst case behavior, that is already shorted. Your array is already shorted either in ascending or descending order. So the worst case behavior is order of n square. Okay. When the best case occurs, any idea when the best case of quick short occurs?
Sir, when every time the array is divided in half,
So
it's a
balance.
balance.
So the when the array is totally balanced, every time you can divide the array into equal to halves. Okay, that is the best case. So this is the quick short function. So first of all, if you are asked to write the quick short and to explain the quick short with the help of example, so first of all you have to write down this quick short function, then you have to write the partition function. Okay. So quick short, three arguments are there, APR. So first one is your array, second one is your uh, first index, and then R is the last index. So if P is less than R, this is quite natural. Your first index is obviously less than your last index. Okay. Then you have to call the partition function and you have to store the result of the partition function in the variable Q. Okay. Then third line calls the quick short, recursive version of quick short, that is A, P, and Q minus 1. That is the left subarray. Okay. After the completion of the third step, you can go for the fourth step, that is right subarray. So A, Q plus 1, R. So initially Initially, this is your array. So initially, this is your array. This is the array index P, and this is the array index R. Okay, right? Now, obviously, P is less than R. So then Q, then the first line, after the first line, the second line, Q is equal to partition of APR. So actually, Q is your pivot point. You have to place the Q in its proper position. Second line, it represents the placement of the pivot point, pivot element in its appropriate position of the array. Okay, so this is your Q. This is your Q. Okay, so every elements in the left sub array are less than is equal to Q, and every elements in the right sub array, every elements in the right sub array are greater than, these are greater than Q. Okay, is it fine? Then that is, you can divide the array into two parts. So what is the first part? What is the first part? So first part starts from array index P and ends with array index Q minus 1, ends with array index Q minus 1. Okay, and this is your Q, this is your Q, and finally the right subarray. What is the right subarray? This is the right subarray, that is starts from Q plus 1 to R. Okay, so this is the dividing step. Then you have to conquer, that is, you have to solve the problem. So here in the conquer step, you have to use the recursion. Finally, you have to combine. Okay, so can you suggest me what will be the cost function for division and conquering and combination of the result? What will be the cost? Any idea?
N.
Order of?
N only.
Yes. So the total function is order of n. Okay. That's why this will be order of n extra cost. So T of n by 2, we have to take two parts. That's why 2Tn by 2, and this will be Tn. So this is the recurrence relation. This is the recurrence relation of the quicksort. Okay. Now, in the partition function, first of all, we have to store the last element, that is the pivot element. We are using the Lomoto partitioning. So last element in the variable x, actually your x is returned, and I is equal to p minus 1. So first index minus 1. J runs from first index to last index minus 1, r minus 1. Next, you have to check whether every time your array elements are less than is equal to your pivot element or not. If so, that is, if less than is equal to, then first increment, this is your first task, first increment the value of I, then exchange. Okay, finally, after the completion of the 3 to 6, that is for loop, you have to exchange the I plus 1th element with the last element, rth element. Okay, and return the I plus 1. Okay, now let us take 287 to next 87 2871 2871 3564 3 5 6 and finally 4. So what will be the P? This is your P and this is your R. So this will be 0, 1, 2, 3, 4, 5, 6, 7. So array size is 8. Okay. So this is your array. Okay. Now, first line, if P is less than R, so 0 is less than 7. Yes, true. 0 is less than 7. True. First index less than 7. Last index. Next, partition function will be called and the result is stored in Q. So what will be the value of partition function? You have to call the partition function. So here, what will be the value of X? So X is equal to AR. What will be the value of X?
4.
4. So 4 is stored. Okay. Next, I is equal to P minus 1. Second line. I is equal to P minus 1. So this is let this is I. Next, J runs from P to R minus 1. So J runs from P. So this is your J, right? Okay. Now, if AJ is less than X, so what will be the value of AJ in the first iteration? What will be the value of AJ?
2.
So in the first iteration, AJ, so first iteration AJ will be your 2. So 2 is less than 4. 2 is less than is equal to 4. Yes, this is right. So what should we do? First we have to increase the value of I, then exchange AI with AJ. So I is increased first. So I will be now at this position. Then you have to exchange AI with AJ. So AI with AJ means 2 is exchanged with itself. Okay. Is it fine? Then increment the value of J. Okay. So 8. 8 is less than is equal to 4. You have to check every time this if block number 4. If AJ is less than is equal to X. So 8 is less than is equal to 4. No, false. Then what should we do? Increment the value of J. 7. Are you getting this?
Yes, sir.
Yes, sir.
Yes,
7 is
sir.
7 is less than is equal to 4. No, false. Increment the value of J. So 1. 1 is less than is equal to 4. Yes, true. What should we do?
Exchange.
Wrong answer. First increment the value of I, then exchange. First increment the value of I. This is the line. If AJ is less than is equal to X, then line number 5 is executed first. I plus plus, then exchange. So I plus plus, that is I will be in this position. Then exchange the value of AI and AJ. So AI and AJ are exchanged. So exchange these two values. Is it right?
Yes, sir.
So this will be your 1 and this will be your 8. Okay. Next, J will be incremented in this position. So 3 is less than is equal to pivot element, last element 4. Yes, true. Then what should we do?
Increment I and then
Increment the value of I. So increment the value of I. Okay. And then exchange. So 7 and 3 are exchanged. Okay. 7 and 3 are exchanged. This is 3 and this is 7. Okay. Next, increase the value of J. So J will be at this position. So 5 is less than is equal to 4. False. Increment the value of J. So J will be at this position. So 6 is less than is equal to 4. False. So J will stop in this position because this is R minus 1. Okay. Now what will be the next step?
A of I plus 1.
Exchange AI plus 1 and AR because the for loop is already done. So exchange AI plus 1 and AR. So exchange, you have to exchange AI plus 1. So this is your ith position. So I plus 1 and the final element, last element. So exchange these two elements. So this will be 4 and this will be 8. So this will be 4 and this will be 8. So this is the partition exchanged. The last element is the pivot. Pivot is placed according to low-motor partitioning. Pivot element is the last element. We are placing the last element in its proper position. So every elements in the left subarray are less than is equal to AQ, that is 4, and every element in the right subarray are greater than 4. Is it fine? So this is the quick short. Then you have to recursively call the 213 and 7564. Can you do that 213 or I will explain? Can you do that 213?
Yes, sir.
So then you have to call the third line. So 4 is placed in its proper position. That is line number 2 in your quick short is done. Then you have to execute line number 3, then 4 recursively. Okay. So this is the quick short function, sorry, quick short program. Is it visible?
Yes,
Yes.
sir.
So,
So this is the quick short function, 3 argument function. First one is your array and first index and last index. So if P is less than R, first index is less than last index. So partition result of the partition function is stored in the variable Q. Then you have to call the recursive version of for left subarray and right subarray. Okay. So right subarray is A, Q plus 1 and R. Okay. So this is the quick short. This is the quick short function. So actually this is your algorithmic version and this is your program version. Next, partition function, 3 argument function. First one is A, next second index and then third index. Okay. So this is your partition function. We have to implement the algorithmic partition function into program. So x is equal to a of r. So x is equal to a of r. Here x is equal to a of r and I is set to p minus 1. For j runs from p to r minus 1. And if aj is less than is equal to x, line number 4, aj is less than is equal to x, then first increment, then exchange. Okay, so first increment the value of I, then exchange ai and aj. Okay, you can also use the swap function using some pointer sense. Then finally the for loop, the completion of the for loop. So this is the completion of the for loop, line number 3 to line number 6. In line number 7 you have to exchange the ai plus 1 with ar. So here we are implementing the exchange ai plus 1 with ar and finally we return the value. Okay, so this is the main function. Inside the main function, line number 40, we call the quick short. Here the array index starts from, that is p is equal to 0 and r is equal to n minus 1. N is the size of the array. Okay, now we have to run this program. So enter the array element size. So array element size is 8 and 2871. 2871. Okay, 2871. then 3 5 6 4, 3 5 6 4. So before sorting, this is the array, and after sorting, this is the array. Okay, is it fine? Visible?
Yes, sir.
Okay, so this is the quick sort algorithm and quick sort program, and this is your recurrence relation. If you solve the recurrence relation, you can get order of order of either theta or big O or big omega. That is order of n lgn. In LGN. You can use either substitution method or you can use the recurrence tree. Master theorem is out of syllabus. Both master theorem and recurrence tree are out of syllabus. Okay. So this is the quick shot. Now what is Tower of Hanoi? Any idea about Tower of Hanoi? Tower of Hanoi problem, any idea?
It said there will be a number of disks and
So there will be 3 towers, A, B, and C. Let this is your source, this is your destination. Sorry, this is your destination, and let this is the auxiliary. Okay, so there will be n number of disks in the source. The problem is that you have to transfer the disk from the source to the destination using the auxiliary, but there are two constraints. First constant is that you can move only one disk at a time. Number two, always place the smaller radius disk upon the larger radius disk. Okay, so what is the complexity for this particular problem? What is the complexity?
2 to the power n.
So 2 to the power n. So 2 to the power n, that is exponential. How many moves are there for moving the n number of disks from source to destination? This is the complexity. How many moves are required? Any idea? 2 to the power n.
Power minus 1.
2 to the power n minus 1 number of moves are required. Okay. So here you have to call. So this is the Tower of Hanoi problem. So this is the move function. So first argument number of disks, second argument your source, and then destination, and last one is the auxiliary. If n is equal to 1, there is only one disk, then move the disk from the source to the destination. Okay. Otherwise, you have to move the n minus 1 number of disks from source to the auxiliary. Okay, from source to the auxiliary. Actually, this is your destination, so that's why you have to put auxiliary here. Okay, using the destination, then only one largest, that is largest disk is resides at the source. You have to transfer from source to the actual destination using the auxiliary. And finally, n minus 1 number of disks are at the auxiliary, that is auxiliary is your source, auxiliary to the actual destination using the source as the auxiliary. So there are three recursive calls. Okay, there are three recursive calls. So what will be the cost? What will be the cost of the first line, first recursive call? Any idea? If tn is the if tn is the time taken for movement of n number of disks, then first recursive call will take t of not getting any answer.
T of n minus 1.
T of n minus 1. Second recursive call will take
T of 1.
T of 1. Third recursive call will take
T of n minus 1.
T of n minus 1. T of n minus 1. So what is the recurrence relation for Tower of Hanoi? What is the recurrence relation?
2t n minus 1.
T of n minus 1 plus 1. Sorry, this will be your T of 1. That is T of 1 is 1. Okay.
Okay, sir.
This is your base case. Toroshi, this is your base case in your induction, in your recurrence. Movement of one disk will take the constant time. This is your base case. So again n minus 1. So this will be 2t 2t n minus 1. 2t n minus 1 plus 2t n minus 1 plus 1. Can you solve? Can you solve it?
Yes, sir.
If you solve this problem, then you can get order of 2 to the power n. Order of 2 to the power n. The complexity is 2 to the power n. The complexity is 2 to the power n. So if you solve this problem, then the output will be 2 to the power n minus 1. 2 to the power n minus 1. The output is 2 to the power n minus 1. Actually, 2 to the power n minus 1 is this is your final result. And we are discarding the constant value. That's why the complexity is order of 2 to the power n. Okay. Now this is the 2 to the power n minus 1 is the number of movements. What is Tn? Tn is the number of movements. Okay. For moving n number of disks. So output is 2 to the power n minus 1. If here in our example there are 3 disks. So how many moves are required? How many moves are
7.
required? 2 to the power 3 minus 1, that is 7. 7 moves are required. Okay. So let us check. So this is the move function. If n is equal to 1, then just move from source to destination. Otherwise, else, that is number of disks are greater than 1, then you have to call the 3 move function. Okay, recursive call. You have to maintain the order. First, you have to move the n minus 1 disk from source to the auxiliary, then the largest disk from source to destination, and finally n minus 1 disk are there in the auxiliary. So n minus 1 disk from auxiliary to the destination. So enter the number of disks 3. So there are 7. 7 moves are there. 2 to the power 3 minus 1. 1, 2, 3, 4, 5, 6, 7. So A to C. First A to C. So first you have to move A to C, the smallest disk from A to C. Okay. So next one, A to B. Next one is A to B. A to B. The next one is A to B. Okay. The next move is C to B. Okay. C to B. So C to B. So move from C to B. Okay. Next one, A to C. So the largest radius disk is move from A to C. Next, B to A. Next is B to A, smallest one. Next, B to C. Next is middle disk is move from B to C. Okay. And last one, what is the last one? A to C. So you have to move A to C. A to C. So total 7 number of steps are required. Is it clear the Tower of Hanoi problem?
Yes, sir.
Can
Yes,
you
sir.
solve? Can you solve the recurrence relation? Can you solve this particular recurrence relation?
Yes, sir.
Okay, then you can get 2 to the power n minus 1. Okay. And finally, evaluate the postfix expression. So evaluate the postfix expression algorithm is that scan always from left to right. Okay. There are 3 gate questions. Answers are 15, 2 and 80. Okay. First, you have to scan from left to right. If you are getting a operand, then you have to put in the stack. You have to put in the stack, that is push, unless and until you are encountered with the operator. Immediately after getting an operator, you have to pop the top element and just below the top element. Okay, then perform the operation and again push the result in the stack top. So this is the main idea for evaluation of postfix. Okay, now you have to perform a C program for evaluation of a postfix expression, Tower of Hanoi, and Quicksort. Okay, so these are the application of stack. Is it fine?
Yes, sir.